these three problems basically follow up on that little bit of quick practice that we did during class yesterday. These go pretty quick. There's not a lot of complexity to them, not a lot of trick. The biggest thing is just kind of taking each letter, each variable, as its own little piece in the problem. So, like in the case of number 1, all of them are x's, which makes our lives a little bit easier. When we multiply the x's, remember we saw yesterday that we add their exponents. So I'm going to be adding their exponents. When I add all these exponents, what do I get? Yes, it's 11. Now the one trick with this one is that you see that it's 11 and not 10, because if you're looking just at those exponents, you might just look at the 6 and the 4 and add those, but if you did that, you would have forgotten and neglected the fact that there's an x in that last part, which has an unwritten exponent of 1. And so we got to include that in there. So yes, that first is x to the 11th. All right, then on to number 2. Same idea, except in number 2 you have a mix of a's and b's. And we're just going to deal with the a's and the b's separately. So I got a there, and I have a there, and I have a there. So there's 3 different a's that I have to combine. Again, multiply them, so I'm going to add their exponents. Remember, of course, that the first a has an exponent of 1 on it, even though we didn't write it in. So I do the 1 plus 5 plus 2, and that's going to give me a to the power of 8. All right, then we head over and we take a look at the b's. Now notice for the b's that we have 2 of them. And so I'm just looking at those 2 now for answering this part. So it's going to be b to the power of, add the exponents. And 7 and 3 gives us 10. So you should have a to the 8th, b to the 10th there. So there's a question about, can't we factor out of this basically, right? Because like 8 and 10 are both divisible by 2. Because the 8 and the 10 are both exponents, we can't. Because remember that 8 isn't the number 8. That 8 actually means that we have 8 a's all multiplied out together here. And then the 10 b's tells me I have 10 b's, which I don't really feel like writing all of them, but I'm probably going to anyway because, hey, I'm diligent like that. So if you look at it written out the long way, is there anything that we can pull out of everything there? No. And so that just helps us kind of see why. It's because it's the exponent instead. All right. Then we head on to that last one where we have the division. And when doing these, it can often be a little bit tricky because there's kind of a couple layers to it. If you try to deal with every single m all at the same time, it's very possible that you're going to run into a possible issue. So what I would suggest instead that you do is simplify the top. So combine the m's and combine the n's on the top. And then do that separately on the bottom first. So make it into a 2-step problem. Oftentimes by just showing an extra step, you make a problem way, way easier. So like on the top, you notice I have a grand total of 8 m's. I'm sorry, nope, 10 m's. I forgot the 2. So that's going to be m to the 10th. And then we have 9 n's. So that's going to be n to the 9th. And that was just from the top. I then go and do the same thing on the bottom. When I do that, I find that I have 12 m's on the bottom and 10 n's on the bottom. Remember, that was just the first step though. The second step now is that I can go ahead and combine the m's that are on the top and bottom, and then go to the n's that are on the top and the bottom. So when I'm dividing, what am I doing again with my exponents? Yep, we subtract them. And so if I go and look at it that way, then for the m's here, I would do 10 minus 12, which would give me m to the negative 2. I don't like m to the negative 2, right? As we saw yesterday, we don't want to leave the negative in there. That actually tells me that I have those 2 m's on the bottom of my fraction. So whenever you get a negative exponent, it's going to tell you to flip it in the fraction. And again, we're going to spend more time with the negative exponents in the future, but we're getting little tidbits of it now. All right, then we do the same thing with the n's. For the n's, it would be n to the negative 1. Well, again, there's a negative, so that tells us that it goes in the bottom. So it would be over n to the 1. I don't really need to write n to the 1, do I? That can just be n. And so it's going to be over m squared n. The question is, what is over m squared n? Because there has to be something on the top. Yep, 1. And so then that is our final answer. I at least find these way easier by going through kind of an intermediate step like that. Otherwise, it's easy to lose track of a number along the way or something like that. Besides, even if you try to do it all at once in your head, you probably in your head are actually creating this. You're probably adding the stuff on the top and bottom separately, and then you're doing your subtraction anyway, so you might as well write it out to make sure that there's no little mistakes that happen along the way. As a general rule, when you look at these types of problems, if there are more m's on the top, then you will end up with m on the top there. If you have more m's on the bottom, then your m will end up on the bottom. Same for, of course, all the variables. That's a nice general rule and a way to be able to check yourself to make sure you're putting this stuff in the right spot. So yesterday we actually saw what this sort of a thing means. Yesterday at the start, if I had just given you 125 to the power of 1/3, you would have had no idea. But based on the work that we did do yesterday, we actually can do this. So go ahead and write it down first, and then we'll see how and why we can do that. All right, so yesterday, we saw what a fractional exponent means. Yesterday, into our notes, we saw that writing something like 125 to the power of 1/3, same thing that like you did on the assignment, that's the same thing as writing the cube root of 125. Technically, behind the scenes, we started by making it cube root of 125 to the power of 1. That's where that 1 went up here. But of course, we don't have to write 125 to the power of 1 because that's just 125. So really, this question is saying, what's the cube root of 125? That should seem like a familiar question, right? We took a look at this one yesterday. Because we are saying, what number to the power of 3 equals 125? And I asked you yesterday to get that value memorized. So what number cubed equals 125? 5. And so for this first one, 125 to the power of 1/3 equals 5. No calculator needed. All right, next one. We can also do this one without the calculator, but you're going to see that we have to get a little bit fancy with it. If you haven't written it down, of course, write it down. And then, once again, I see that we have a fractional exponent. And anytime I see a fraction in my exponent like that, I know that I'm going to be going into a radical. And so if I just start by writing this as a radical, you should get the square root here of 4 to the power of 5. All right, now that I have those, there's just one little problem. I don't know what 4 to the power of 5 is. Well, the nice part is that we can actually reformat this to make it work a little bit better for us. Because I could write the square root of 4 to the 5th, or I could write this as the square root of 4 to the 5th. Both are valid. Now, which one of these is easier to use here? Which one of these can you do without a calculator? Can you do 4 to the 5th without a calculator, or can you do the square root of 4 without a calculator? Square root of 4, right? And so that's what I'm going to do here. This is way more useful to me by writing it in that order. It allows me to do the mental math with it. All right, so then square root of 4, of course, that's 2. So this is then 2 to the power of 5, which is a value that we should know. What is 2 to the power of 5? 32. That is on your list of values to memorize. If you are still working on it, keep working on it. You're going to want to know those because they do come up so often. All right, so for the last one now, we have a fractional exponent. So of course, the very first thing we do is we write it as a radical, but we have a choice about which way we want to write it. You can write it either with the radical over the 27 squared, or you can write the radical over the 27 and then square that. So the question is, which one of those two is easier to do without a calculator? Well, which one can you do without a calculator here? Can you do 27 squared, or can you do the cube root of 27 without your calculator? I hope you can do the cube root of 27 without your calculator, because that's actually one of the values we should know. Because we should know that 3 cubed equals 27, and therefore the cube root of 27 is 3. So really this question is saying, what's 3 squared? And 3 squared, of course, is 9. And so that's our final answer. So it's a little bit of creative use of our rules. allowing us to do something that we wouldn't have been able to do otherwise. All right, now we come on to these types of problems, and these problems are actually going to bring together multiple little veins of work that we've been doing into one single problem, as you're going to be seeing here. So the first thing that I want you to notice is that we're trying to multiply different radicals. These both have different indices. One's a cube root, the other one's a ninth root. That means that we can not just combine them into a single radical. There's no way that I can just in one swift move turn this into one answer where I have x to the power of something. Like you might be thinking that it's like, well, is it the 12th root of x cubed or something like that? No, it's not. If only it were that easy, and it's not. So instead, we need some way to be able to do this. Now, when I multiply variables, I know what to do with their exponents, but I don't know what to do with their radicals. But the nice thing is that we know what a radical is as an exponent. So the very first thing we're going to do when we see one of these problems where we have to operate on the radicals is we're going to rewrite each of the radicals as exponents. So for instance, I have the cube root of x squared. I'm going to turn that into x to the power of a fraction, because of course a radical gives us a fraction exponent. And remember that the exponent goes on top and the index of our radical goes on the bottom. So that's going to become x to the 2/3. Then we do the same thing with the ninth root of x, where I'm going to write that part of it as x to the power of 1/9. So step one, I just change it from radical form into exponential form. Why? Because at least now I know what I'm supposed to do with those two exponents. Because when I multiply the variables, what do I do with the exponents? Yes, we add them. And so that's what we're going to have to do here. We're going to have to figure out what 2/3 plus 1/9 is. As you may recall recently, you had an assignment. It was actually our recent WAMAP assignment. It had you practicing how to do operations on fractions, including adding fractions with different denominators. Now you can see why. We were getting ready for this. Oftentimes I'm going to be building up little skills that are going to be coming up in the next week, and such was the case with that as well. All right, so I'm adding fractions. What do I need in order to be able to add fractions? Yep, the bottom numbers have to be the same, which we call common denominator. If you're thinking common denominator, that's what that means there. So we need those bottom numbers to be the same. All right, so right now it's a 3 and a 9. What do I want my bottom number to be on the next step? I want it to be something over something. All right, what do I want the two bottom numbers to be this time? Yeah, it looks like the simplest way is 9, because I can turn the 3 into a 9. So I'm going to make both of these into 9s. And by the way, if you have a little bit of trouble with the whole adding fraction things, notice the order I'm writing it in. I start by just knowing there were two fractions being added, then I fill in the denominators, then I'm going to put in the numerators. This is a great order to do it in because it helps prevent certain mistakes, at least, if you have trouble with these. All right. Now, of course, this part, this second fraction, that one's going to be really easy, right? Because it's already 1/9, so we don't need to change anything there. But for the first one, what am I multiplying this 3 by in order to turn that into 9? 3 times what is 9? 3. Now the key with doing these is that remember that whatever we multiply by the bottom, we have to multiply into the top as well, which is why this is then going to be 6/9. All right, and now that we're here, we go ahead and we do the addition. A cool rule of math, I don't know if you've noticed this pattern, but anytime we say that two things have to be the same, like we have to have the same denominator here, it's because after we do whatever it is that we're trying to do, it's going to stay the same. So we need a common denominator because our answer is going to be over 9. And then we just add on the top. So we get 7/9. Now remember, why did we do all this? Because when I multiply the x's here, I add their exponents. So this is all just work over here showing why we get x to the power of 7/9. This is how we add the radicals. We first turn them into the fractional exponents, Then we can add those exponents. And now I just have a single term. Now, I don't want to leave the fraction exponent there. I have to then turn it back into a radical. So last step, we rewrite our x to the 7/9 as a radical, which, after the work we did yesterday, is hopefully fast and easy. You should be getting the 9th root of x to the 7th. As you might expect, the next problem is going to be somewhat similar because in this one, we again have a radical and a radical. The only difference is that this time I'm dividing instead of multiplying them. The only difference that's going to mean then is that instead of adding my exponents, I'm going to be subtracting my exponents. That's about the only difference. Our process is still going to be the same, where we're going to be turning them both into fractional exponents. Then we will do the subtraction of their fractions, and then we'll turn it back into a radical. So with that in mind, before we do it together, please work that one through yourself, and then we'll come back together to look at that answer. All right, so we work it through, we do the subtraction, we end up with 2/6, but something jumps out to me about this answer right away. It reduces. Whenever it's reducible, yes, reduce it. So I'm actually going to be doing this as 1/3, not 2/6. And so I know that my answer is x to the 1/3, and I just need to put that back into radical form, which is, of course, then the cube root of x. And that's our final answer again.